All right, so this is Physics 1510, Chapter 11, Part 2. We're going to keep working through the notes, looking at more examples, and looking at some additional concepts. First thing I want to show you is kind of applying Q equals MC delta T and Q gained equals Q lost to a slightly different situation. And this is a particular trick that, historically speaking, has been very handy within the scientific community, namely in metallurgists and chemists trying to identify what something is made out of. Because you see, every single material has a unique specific heat. So if you can perform an experiment where you can test a certain object and calculate experimentally what its specific heat must be, then you can compare it to a table of specific heats to try to figure out, sort of in reverse, what the object is made of. You can calculate its specific heat, you can compare it to known specific heats. And that's going to be the example we do right here. A metallurgist heats an unknown solid of 100 grams. It is a unknown grayish metal up to 800 Kelvin and drops it into a 1 kilogram bucket of water. The water begins this whole process at 25 Celsius and will end at 26.5 Celsius. So it increased by 1.5 degrees Celsius. Based on the information provided here, what is this material most likely made of? So the tactic here is we're going to use Q equals MC delta T and Q gained equals negative Q lost, combine them again like we did before, the goal being to try to solve for the specific heat of our unknown material. So I've set things up very much the same way as before. On the Q gained side, we're going to replace that with the information of the water, since in this exchange the water is going to gain thermal energy from the hot metal. So on the water side, we've got the mass of water, the specific heat of water, and the temperature change specifically of the water. And therefore on the right side, since the metal sample is going to be losing thermal energy, we have put all of the metal data there. Mass of the metal, the unknown specific heat of the metal, and the temperature change of the metal. And out of all of this, the only thing we actually don't know is the specific heat of the metal. So we don't have to look anything else up. We're good to keep moving forward to solve for specific heat of our unknown metal. Plugging in mass of the water, 1 kilogram, specific heat of the water, 4,186. Temperature change of the water, it ends at 26.5 and it started at just 25. So that's a change of positive 1.5. Since it's delta T, we can use Celsius. On the right side, we do know the mass of the metal. 100 grams is 0.1 kilograms. We keep the negative out front. C is unknown. That's what we're going to find. And then lastly, the metal's temperature change. The metal's going to get colder. It started real hot, and it's going to cool down in the water. One small trick here is the question gives the metal's starting temperature as 800 Kelvin. Because this formula has a delta T in it, you are allowed to use either Celsius or Kelvin, but you cannot mix and match. For delta T, if you plug in, a Kelvin temperature for T initial, you would also have to use a Kelvin temperature for T final. Or alternatively, if you use Celsius for one of them, you have to use Celsius for the other. Both are legal, but you can't mix and match. So what I've done in my work here is I plugged in 26.5 Celsius for the final temperature, and our initial temperature, I've converted the 800 Kelvin into its equivalent Celsius temperature. So take any Kelvin temperature, subtract 273, and that will give you the relevant Celsius temperature. So our initial Celsius temperature for the metal is 527. That is subtracted from positive 26.5 for the metal's delta T. We need to factor through the negative as we did before, but again, the only unknown currently left here is C of the metal. So the entire left side can condense down to 6,279. Everything on the right side can condense down to positive 50.05 times our unknown c. We can solve for our unknown c, which is going to be 125.45 joules per kilogram degree Celsius. And now that we have that number, we can take it over to our table here and look at what materials it is closest to, what values on this table rank closest to this number that we found. The two closest ones are lead and gold, and this is where a little bit of problem solving, critical thinking needs to come into effect. The problem did tell us the metal was grayish. So of these two entries that are closest to our number, only lead is grayish. So that most likely means that this sample was made out of lead, and that means that the water has now been contaminated by lead and needs to be dealt with accordingly. So, again, this is a sort of classic trick that scientists used to identify things back before we had other tools and techniques available for that. So, pretty handy trick. All right, so our next concept, next thing that we're going to cover within Chapter 11 is going to be phase change. And before we start looking into the math behind that, we're going to look into the math behind that. First, I want to look at these statements and sort of think about them, because some of the math behind phase change doesn't necessarily compute with how a lot of people tend to think about phase change. Now, phase change refers to the act of some object changing the state of matter that it's currently in. Melting, evaporating, freezing. All these things where solid, liquid, or gas will transform into one of those other forms. Now, I want us to look at these statements here real quick and just ponder them for a second. Melting is a cooling process. Freezing is a warming process. Condensing is a warming process. And boiling is a cooling process. I want you to ponder for a second whether or not these statements make sense to you, if they kind of track with how you understand how phase change works. And it might not seem like it, but these statements are technically true. They're just not from the perspective of the object that is undergoing the phase change. Now, phase change is basically thermal expansion taken up to its logical extreme. If you have a pot of water that you are boiling, you are adding thermal energy to it, you are constantly making the particles in that water more and more excited. Those particles are naturally going to drift further and further apart. You may have even seen the water level of a pot of water rise slowly as you begin heating it until it starts boiling. Eventually that water is going to hit its boiling point. It's going to start bubbling and steam is going to start coming out of it. And as you keep adding thermal energy to it, it's going to keep evaporating more and more and more. More of that liquid water will turn into gaseous steam. And what happens as that phase changes is each of the individual water molecules absorbs more thermal energy from its surroundings, and slowly those particles become so energized, they bounce off of each other so hard and so fast that they begin drifting away from each other, so far apart that they can no longer maintain a liquid state. A gas is literally just a liquid that's been spread so far out that it isn't a liquid anymore. It's expanded beyond what it could hold itself together as a liquid. And the steam, the water, needed to absorb thermal energy in order to make that happen. But since the water absorbed thermal energy, it itself absorbed more energy in order to undergo that phase change, that energy had to come from somewhere. Something else had to lose thermal energy just so that the water could evaporate. Therefore, even though the water absorbed energy to become steam, therefore you'd think of that as warming up. From the perspective of the universe surrounding the water, from the water's perspective, it's gaining energy and it's evaporating. But from the perspective of the things around the water is sucking thermal energy out of those things in order to become more energized and to turn into steam. So that means when water evaporates, it technically cools off its surroundings in doing so. It has to absorb heat from its surroundings in order to evaporate. And this is why humans sweat. The entire reason that humans sweat as a means to cool us off, it's not just to put liquid water on your skin. The reason that we sweat is because when there is liquid water on our skin, and humans are already pretty warm. Humans are warm, therefore the water coming out of your skin is already going to be pretty warm. And then if you're outside on a hot summer day, it's just going to get even warmer. And that water on your skin needs to absorb thermal energy in order to evaporate. On a hot day, it wants to evaporate, but it needs to absorb energy in order to do it. And since that water is touching your skin, you are the thing it's going to absorb that thermal energy from. So the water evaporating off of your skin does actually cool you down, because in order to evaporate, the water needed to absorb thermal energy from you to complete its phase change. The inverse is true of condensation. Condensation is the term for what happens when a vapor turns back into a liquid. Speaking of hot summer days, imagine you take a nice ice-cold glass of iced tea outside with you. It's a glass. The glass is made out of glass. It's not insulated or anything. You have iced tea in it, and as you leave your beverage out to sit, eventually water droplets start forming on the surface of your drink. That is condensation. That's water vapor from the air touching your cold container and condensing back into liquid on its surface. It's kind of annoying when it does that. For one, it makes your glass slippery. For two, the water can spill everywhere and ruin the counter you set it on. But it also makes your drink warmer. Because in order for the water to evaporate into steam, it had to absorb thermal energy first. For steam to turn back into water, it has to release thermal energy. And specifically, if the vapor is condensing on your ice-cold beverage glass, then it's releasing its thermal energy into your beverage, which just makes it warmer. So, all of these statements currently on the slide are true. They're just from the perspective of the surroundings of the object. We talked about boiling and condensing. Well, let's look briefly at the other two that are here, melting and freezing. When something melts, when ice melts into water, it has to be absorbing thermal energy from its surroundings because it needs more thermal energy. The way that phase change between solid and liquid works is solid objects, the molecules are pretty well locked in place. They're still able to move, but they have sort of a structure to them. But as you energize the particles of a solid object, they'll start drifting further apart, and therefore the bonds between them become a little bit weaker. And so what was once a solid, as its particles drift apart and move around more, suddenly becomes liquid because the particles are too far apart to maintain a solid form. In the case of ice melting, as ice absorbs thermal energy, its particles drift further apart, the unique structure that makes it ice breaks down, and it becomes water. It has to absorb thermal energy to make that possible, meaning that the process of melting cools off the surroundings of the ice. If you hold ice in your hand, it's gonna start melting, and it cools you down. It takes thermal energy out of your hand to put it in the ice to then melt it. The reverse is true of freezing. The slide says that freezing is a warming process, and this is, in fact, the case. It's the inverse of what I just said. If you put something in your freezer, to freeze it, then it has to lose thermal energy in order to, if it's a liquid, it has to lose thermal energy so that its particles slow down, move closer together, and lock into a solid form. Since the object is losing thermal energy, the surroundings must gain it. And this is why the actual machine of a freezer, its function is to take thermal energy out of your food, take it out of the freezer itself, and put it someplace else. So all these statements are true. They're true from the perspective of the surroundings of the reaction. And science has a few different terms to describe the process of whether or not something gives off heat or absorbs it. Those words are endothermic, if a process involves absorbing thermal energy, and exothermic, if a process involves giving off thermal energy. You may have heard these terms before, depending on how much chemistry you've had. So, of the 4 phase changes we're going to be studying in this class, melting and boiling are endothermic because they pull thermal energy into the object, whereas freezing and condensing are exothermic because, from the perspective of the object that is doing the freezing or the condensing, it's giving off thermal energy. So let's look a little bit at the math behind phase change now. Now, think for a moment, if you're trying to freeze some water into ice, would it be easier to freeze a small amount of ice or to freeze a lot of ice? You know, if you have a bucket of water versus a single ice cube's worth of water, which one's easier to freeze? In order to freeze the whole bucket of water, then you need to remove more thermal energy from it because it has more mass. And since it has more mass, there's more particles in there that have enough energy to keep them at their current temperature. So the more mass something has, the more energy you have to remove from it to actually cause a phase change. And that leaves us with the 2 formulas that are currently on the screen. These 2 things are the phase change. It's really the phase change formula. There's just 2 slightly different versions of it. And the variables here are Q equals M times L. Q is still heat flow. If you are adding thermal energy to something to, say, try to melt it, Q would be positive. If you're trying to remove thermal energy from something to freeze it, Q would be negative. M is the mass of the material that you are attempting to make phase change. The mass of the object does matter. The amount of material present matters. And then L in general, I'll talk about the differences between LF and LV in a second. L is the latent heat the latent heat, excuse me. L is a new variable. There's going to be a lot of those, sorry. L is the latent heat of a certain material. And kind of like how every different material has a different specific heat, every different material has a different latent heat. And latent heat refers to the amount of energy needed to be removed from something in order to induce a phase change. So, well, let me just go ahead and put some numbers on screen. Let's look at the latent heat of fusion column right here. There's different numbers in this column to represent how much energy is required to melt any of these materials currently listed on the side here. So, the bigger something's latent heat of fusion number is, the more energy needs to be added to it in order to melt it. Or, alternatively, the more thermal energy needs to be removed from it in order to freeze it. Of the materials currently listed here, there's lots of different ones. We've got helium, nitrogen, oxygen, things that are very commonly found in gaseous form on planet Earth. But we've also got things like water and some solid metals as well. The lower numbers on this table, the absolute lowest number on this table, is the latent heat of fusion for helium. It's the only one here that's times 10 to the third. That makes it the smallest one here compared to, say, the latent heat of aluminum, I think that's the biggest one here, which is times 10 to the fifth. So helium has a relatively small latent heat of fusion. That means that it doesn't take as much energy to melt helium as it takes to melt aluminum. And that's one reason why helium is usually found as a gas on planet Earth. Meanwhile, aluminum is usually found as a solid. It's easier to evaporate helium for several reasons, but this is one of them. It's easier to melt helium, which is why you never find solid helium on planet Earth. Just the ambient temperature of Earth has given it enough thermal energy to get it into a vapor form, whereas for aluminum, the natural ambient temperature and energy of Earth is not enough to keep it regularly out of solid form. So every different material has a different latent heat of fusion. And if you wanted to know how much energy was required to take a block of aluminum and melt it, then you'd look on this table for the latent heat of fusion for aluminum, and you would multiply this number by the mass of aluminum that you have. So those are the two factors that affect how much energy is needed to melt something, or how much energy needs to be removed in order to freeze something. So the latent heat of fusion determines the energy requirements for both freezing and melting. Now there is another type of latent heat. There's a second version of the formula here that's LV instead of LF. And LV is called the latent heat of vaporization. Latent heat of fusion covers the energy requirements for melting and freezing, specifically the solid and liquid phase change. Latent heat of vaporization covers evaporation and condensation, specifically the energy requirements for going between solids. I misspoke again. The energy requirements for going between liquids and gases. And that means that if you were, say, studying the phase change of water, you would need to use a different latent heat depending on what phase change it's currently undergoing. If it's melting, you'd want latent heat of fusion. If it's evaporating, latent heat of vaporization. Every single material on this table has a different latent heat. And again, technically every material has two different latent heats. You never have to memorize any of them. You will have access to this table whenever you need it. I promise you that. Don't have to worry about that. For right now, before this little brief sub part of the chapter ends, let's look at how we would use these formulas, this information. So let's say that we have some amount of ice, of negative 10 degrees Celsius ice, and we want to evaporate it into 110 degrees Celsius steam. In order to get that ice into that steam, it has to undergo two separate phase changes. And the graph currently on the screen is designed to represent the energy requirement to cause all of those phase changes to happen from start to finish. But not just the way that the phase changes, the energy requirement of the phase changes, there's also the fact that you have to change the object's temperature as well. So let's say that you start with your ice. We're going to start with ice. We're going to start here in the very bottom left-hand corner of this graph. Ice is the coldest state of matter that water can occupy. And if you have negative 10 degrees Celsius ice, it's below freezing, it's currently ice, it'll stay ice until something changes. If you add thermal energy to that ice, if it's at negative 10 degrees, does it immediately begin melting? No, it's going to start warming up. So the first little part of this graph here shows that if you have solid ice and you add energy to it, the horizontal part of this graph represents adding energy to the object, whereas the vertical axis represents its current temperature. If you have ice that is below freezing and you add thermal energy to it, if you add thermal energy, then the ice's temperature will rise. You will warm the ice up, and this will continue until you hit 0 degrees Celsius, the melting point of ice. So, if it's below its freezing point, you add thermal energy, you're going to warm it up, and you're going to warm it up until you hit its melting point. Melting point and freezing point are the same thing. I use them as synonyms, my apology. You will warm that object up until you hit its melting point. And something weird starts to happen at the melting point. Well, for one, it starts melting, but something additionally weird starts to happen. MC delta T tells us it'll take a certain amount of energy to warm our ice up from -10 up to 0. We can use that formula to figure out how much energy is needed to get it from -10 up to 0. But once you hit 0, that's when melting starts. And the weird thing is, and this is true for all materials, it's not just water, all materials, once they start a phase change, they don't change temperature again until they're done with that phase change. Ice doesn't stop being 0 degrees Celsius until it's completely melted into water. Ice caps out at 0 degrees Celsius. You have to keep adding energy to the ice to melt all of it. And then, once all of it is melted, if you keep adding energy, it will then increase its temperature again once it's completely water. Ice, 0 degrees Celsius, is the point, the temperature at which ice and water coexist. Ice can be 0 degrees Celsius and water can both be 0 degrees Celsius. And at that point, both can exist. You can have both in this in-between state, but you have to complete the phase change one way or the other in order to continue changing its temperature. Because once you get the ice to 0, its temperature stops changing because that's the highest point, that's the highest temperature that ice can exist. So once you get the ice up to 0, all the thermal energy you add after that point just goes into melting the ice until it's done melting. And so that's why on this graph, the temperature, the graph flatlines for a minute. Temperature stops increasing until the phase change is done. Once the phase change is done, once you've added enough energy to completely and successfully melt all of the ice, once it's now completely 0 degrees Celsius water, then if you keep adding more thermal energy, then its temperature will continue to rise. It's now water, you're adding heat to the water, it'll get hotter. So once it's 0 degrees Celsius water and you add thermal energy, it will continue getting warmer until you hit its boiling point. At the boiling point, we've triggered another phase change and the same thing happens. The water, once it hits 100 Celsius, stops getting hotter. It caps out at 100 degrees Celsius, and now that the phase change has started, all the thermal energy that you add to it will just cause the phase change, will just allow it to turn into steam. So, same as before, the graph tops out for a second. Its temperature stops increasing until the phase change is complete. And this is why boiling things in water is a handy way to cook them, because boiling water does not get any hotter than 100 degrees Celsius. It remains 100 degrees Celsius until it's done evaporating. So that's a nice confirmed high temperature that won't change as long as it's still boiling. And it's going to keep boiling as long as you keep adding energy to it, and its particles are able to space apart and slowly turn into steam. So just as before, you have to complete the phase change. You have to give it more energy in order to turn it into steam. And then once all of it is steam, you can add more thermal energy to it again to make it the steam warmer. This is one reason why steam burns are a nasty thing. If you haven't heard of steam burns or you haven't heard that they can be nasty, they can. And the reason is, I am not recommending this. I'm just giving an example. Don't do this. If you were to stick your hand in boiling water, 100 degrees Celsius water, that would hurt. That would be bad. You'd get a scald burn. But that would be less dangerous than being blasted with 100 degrees Celsius steam. Because by virtue of the fact that the steam has undergone this phase change, it's absorbed enough energy to become steam. That means it has more thermal energy than 100 degrees Celsius water does. Even if they're the same temperature, the steam has more energy in it because it's undergone the phase change. And because it has more energy, it's able to give off more energy. So this is one reason why steam burns are exceptionally nasty, because by virtue of being steam, the steam has more energy than the water does. So steam's dangerous. Be careful. Now, everything I've just said about how you have to keep adding it during the phase change, temperature stays the same, and you keep adding energy till the phase change completes, and then once it's complete, temperature rises. This is true if we were going backwards down the table. If you were starting at steam and wanted to turn it down into water, turn it down into ice, you do all these same steps I mentioned. You just do them in reverse. You need to cool down your steam to 100 Celsius. You need to remove enough energy to turn the 100 degrees Celsius steam into 100 degrees Celsius water. You'd have to then remove energy to cool the 100 degrees Celsius water down to 0 degrees Celsius water. You would have to then remove enough energy from the 0 degrees Celsius water to turn it into 0 degrees Celsius ice. And then you'd have to remove energy from the 0 degrees Celsius ice to reduce its temperature to -10 Celsius ice. In order to do all of those steps, you have to add together all of the thermal energy requirements of every single step in order to do all of them. And we will look at the next part of this video series. We'll have the math for that part. So stay tuned for that. Send in any questions that you have as you have them as you're working, and have a wonderful day.